Why, thank you. And as we say in Texas, howdy. Howdy. Today I'm going to be talking about lessons learned in how to conduct field work based on my experience at 17 disasters and over 35 exercises. It's really an honor to be giving the talk for this section, as the collection of your papers represents excellent work conducted under the hardest condition in robotics, the field. Field work is different, as you know, from laboratory work in at least two ways. The data that you get is different in terms of authenticity, the quantitative measurability, and the repeatability of the data. And you need to collect a wider variety of the data, especially to capture any human system effects and the impact of the environment. So I'd like to begin by discussing where field robotics, field work fits in the pantheon of the scientific methods. So science has typically relied on humans observing and assembling a corpus of case studies of phenomena, and then getting to a point where they could identify trends and extract principles to go back and test. So you know the story about Isaac Newton looking at an apple falling and sparking his interest in gravity. That's a classic example of the observation of the natural world. And then we can look at Galileo, again, continuing the physics, conducting the experiment of a staged world experiment. In this case, stage doesn't mean like theater stage, although he was doing a little theatricality there, doing this from the Leaning Tower of Pisa. But what he was doing was trying to pare down the experiment to something, the observation that could be observed and seen, and get the macro effects, to see at least get the first order effects. Of course, nowadays, when you think of physics, or at least when I do, I think of things like the CERN accelerator. I mean, you're talking about highly controlled experiments, highly controlled conditions, and highly controlled hypotheses, so very narrow. So we've gone from a what the heck are we looking at to macro, and now we're looking at the micro, at single instances of things going on there. And so engineering and medicine has evolved with the same pattern of going from nature back to the lab, coming up with discoveries, and then working forward to produce them and have them adopted. So as the process goes from the corpus of cases about the phenomena, you get more details about what's happening, and you see the scientific methodology increases. So we're going to start seeing, as we go up this, we get more quantitative measures. And we start controlling the conditions, less here, extremely so here. And so we have high repeatability of the data. So the data acquisitions, the results become much more quantitative. Unfortunately for us, robots are different. Okay, we don't have any corpus of cases for the exciting ideas in robots, what's really working, all the possible effects, right? And in disaster robotics, I try to keep a clearinghouse of the known disasters. Please, if you know of any that are not on my list at crasar.org, I'm counting about 40 deployments to disasters. So that's not a lot to extract first principles from about what's going to work and what will not work, or even what are the critical factors that we should be trying to capture so that when we go to a staged world, or we go to that, we'll be able to do the right things in our staged world and laboratory experiments. Okay, robots are also different in that they don't start in the natural world. They're not a natural phenomenon. It's not like we're observing squirrels or sharks or something, an animal, or we're observing gravity. There's some principle of which we're going to observe, get an idea, and then go back and test. They really start in the lab, and they take as we all know, lots and lots of work, even to get a simple piece of software and hardware working together to actually get out and work reliably in the world to even do a staged experiment, much less getting it out into the field. And in my case, with actual responders, where you feel good enough about the system to get it out there. So the robotic development process is actually going in the opposite tradition of physics, most engineering, and most medicine. Instead of going this way, robotics is starting here and then working our way down there. And that also means that we're very much focused on controlled conditions and very limited types of observations. We can't have just crowdsourcing what robots are doing, you know, phenomena and getting up a compendium of natural history the way we can. So it's really changing things up. But if we start in the lab, we lose something. The downside is we lose authenticity. Authenticity, or how much what's really happening, what are the real problems, happens only in the natural world. We only get that there, but starting in the lab, we miss that. And if we go to the staged world, if we're not careful, right, we can accidentally screen out important events, important factors. And so we just don't know if we've identified the underlying dependent variables or control the right independent variables. So for me, there's an even bigger issue with starting in the lab, is that because we're not authentic, we don't know if we're solving the real problems that are going to make the robots that we're working on for rescue, the robots that you're working on, more readily adoptable. I would like to see robots in use within 5 or 10 years rather than 20 years. So are we working on the right problems? And so to me, the solution is not to just keep trying to do it the same way, but to enjoy this intermingling. Take whatever we're learning from robots in the real world and start using that to feed back and tell us how we can better construct our experiments, better construct our robots. And likewise, educate us on what more we can do for our quantitative work. And at the same time, things that we're seeing in the lab, are we seeing those effects whenever we do go to a disaster, or as robots become more adopted for law enforcement and for fire rescue? Are we actually seeing that? Can we be on the look at that? So that gets us to the issue of data. And so the data to make these types of observations, we know a lot of the data, you know, the performance data things, but there's two parts I think that make robots different, even more different. And that's that we need data about the humans, because robots are part of a complex system that includes a human in there somewhere. And we want to characterize the environment. How do we say what environments the particular robot works in? So if you look about the data about the humans, I think of it as the humans can be behind the robot, those are the operators. People can be consumers of the information for the robot. They're less interested in the robot than what it's doing for them. Or they can be in front of the robot, where the robot is physically interacting with them. Now, if you go back and look at the disasters, about 34 disasters I was able to get information on, 13 of them had terminal failures, where the robot failed and the mission had to be aborted. Only rarely did we lose, or that the group using a robot lose the robot altogether. But 50% of those failures were attributed to human error. That's a pretty high number, and I don't think that's just a user interface issue. I think that's valuable data to us as roboticists, saying, where do we need to add autonomy? Where do we think about our design of the system? And so we need to collect that data. So let's talk about collecting data. Here are my recommendations on what to collect. I mean, these are pretty obvious, right? At least this part of the list is. So the log of activity. For us, that's usually written down. Context, what's the picture of the area, the setup, is it working it? What are the winds if it's a UAV? What's the water condition? What is the ground conditions? Robot sensor videos. We try to get both the robot sensor data and the robot state or logs enough that we can actually put it through a simulator and replay the entire event. And then we try to have somebody constantly videotape the robot of what it's doing. And even if we're in an underground situation, that's often an advantage of sending a small robot behind, just so that we can keep up with what's going on if possible. And so this is pretty obvious, right? Well, we're not necessarily as a field good at doing this. One of my students, Brittany Duncan, in 2012 pulled together 18 studies on field studies that were physically trying out in the field of a small UAV of autonomous takeoff and landing. 18 studies. 17 of them gave the vehicle type. Only 11 actually described the vehicle's dimension. Only 12 said the number of trials for their results on how well their autonomous takeoff and landing work. 7 reported the wind conditions, and I think we all agree that for a UAV that seems like that would make a difference. And only 3 said the altitude to which it actually descended or started from their what they considered the end of the takeoff or where they started the landing. So over the years we may have gotten a little sloppy, and let's try to be better about that. Now let's talk about capturing system data. So I always add two more sources of data whenever I can, and that's the human interaction log that I'm going to show you, and I try to get a video of the team. So that means adding an observer, somebody whose sole job is to fill in this interaction log. So you're adding a person, and then a lot of times we just put a GoPro. I feel like our work is just an advertisement for GoPro, but put that on their helmet so whatever they're looking at, whenever something happens, you're capturing that bigger who's doing what, where. And so we can do that in field exercises, and sometimes we can do it at an actual disaster if you have an extra person there. They can just write this thing. And we use this form. And so we have the different roles of what the team members are, and you're just checking off every time you see it. Once you start, is anybody distracted? This slips and mistakes that comes from Don Norman's cognitive science characterization, human-computer interaction of how people make errors. They either were trying to do the right thing, but they kind of screwed it up, they had the right intent, or mistake. They were totally out of sequence in what they were supposed to do. Okay, and we find that a lot, which tells us that AI can help with automating our checklist. Confused or hesitant, that's a clue. What are they confused and hesitant about? Did they ask questions? Bugs, a big one, and ergonomics. You know, one of the classic ones we found in ground robots is nobody could control them once we started wearing gloves, like the people in the field did. And so this requires ethnography, but the advantage of using a sheet like this is that the ethnography is no longer qualitative. At least you're getting some quantitative. Still depends on how on top of it your observer is, but again, we're trying to move from the natural world where it's been mostly qualitative to try to get back into the quantitativeness that we need as researchers. So another thing is that with data, human error isn't always human error. So that human data, you're probably thinking, okay, great, that's going to be useful for designing a better interface. But it actually helps with other aspects. Here's a case where we conducted a radiological exercise at Disaster City. They had hidden, and right in the middle of a room, a little bit over to the side, that blue cylinder about the size of a water bottle. That's a cesium source, radiological source. And we're using a PackBot 510. It's a classic robot for hazardous materials. It's got used extensively at Fukushima. And we're doing nuclear forensics. It's not just doing a survey. It's actually, can you find where that source is? Well, the observer, undergraduate, had no clue, came back and said, you know, it seemed like it took the operator a long time, 30 minutes in a very small room to find this. And you can see it's bright blue. It's like you got a camera. And he kept complaining. I've got in my notes. I kept complaining about it seemed like the readings were more consistent when he was going backwards. And, you know, it's like, but, you know, stupid operator kind of thing. Well, we thought about it. And we said, go back and take our logs. Go back and take our logs. We've got the sensor log, we've got the external pose, we know where the robot was at pretty much every moment in time, and we know where it was relative to where that sensor source was. Well, you know what? The operator was doing better when he was going backwards. The front of the sensor, the front of the chassis of the PackBot actually blocks that sensor. That sensor was built for people to carry in their hands, and so the blocking from a sensor mast or its mounting hadn't really been thought of, because that's not normally how you use some of these sensors. Well, this is interesting not only just as kind of a fun fact. We called over to the Japanese Atomic Energy Agency, and they confirmed this and stuff, since they also don't use this for forensic localization, but we're like, oh, we need to put that on our list. But it also means that if you're trying to design a search algorithm, every sensor you use that's a radiation sensor of that type is going to have a vulnerability that we need to take into account, certain directions that's not going to work. So this is where field work can help, even understand where the human's having trouble, can help with the overall design. So let's talk about how to characterize the environment. Human data is useful for design, but understanding the environment and trying to compare. And so for me, the motivation is something like we've got a UGV and disasters. Out of all of these different ones, this one's about the size of a shoebox, this one is about the size of a golf cart. How do you know which one's going to fit? How do you compare performance? What is the apples and oranges here? And so, but at the same time, it seems very hard to compare, but we do, many of us who work in this field, have a sort of a qualitative, intuitive notion about when you'd use a big one versus a small one and so on. So can we try to quantify that intuition? And being an engineer, I've always liked dimensionless numbers, like the Reynolds number, that tell you when one regime changes, the change in that ratio, at that point something happens and you're in a different regime. So I've been looking at coming up with dimensionless numbers, at least for the scale aspect of characterizing the environment. So if we think of an agent as a human or a robot, they have some sort of characteristic dimension that influences how much clearance they have to have or what their turning radius is. For people, your shoulder width is incredibly important for determining whether you can crawl down a tunnel and whether you can turn around or if you have to back out. And if you have to back out for a worker, that's very dangerous. You go slower. So there's been a lot of studies on that. Now, in terms of the environment, there's some characteristic environment that I would call the cross-section of the smallest opening. So how big is the robot versus how much space has it got to go through? And it's not the nominal or the average case because, as you know, it's the smallest case, the minimum. So the idea is that the relative size of the environment and the agent is going to create regimes of which you can understand what robots are useful for what types of things. So if we look at that, if the environment is large compared to the agent, we often call those human habitable spaces because they're built for people to get around, usually a couple of widths there, maybe a door that's a little narrow, but overall the space is fairly easy to go around. The architectures have worked with this. Or you're outdoors. And I think you see really Fukushima and the DARPA Robotics Challenge is really working on the concept of disaster robots, but applied for the regime of habitable or outdoor cases. The cases that I've been working more and more in, that have started in, and is the restricted mobility regime, or the restricted maneuverability, which in human terms would be a confined space for a human or even smaller. So that's where the robot has only got maybe one body width to turn around in. Okay, so it's automatically restricted. And what's worse about that is that many of our robots have manipulators, they have antennas, they have all sorts of things that can snag, or antennas that can ground out in that kind of 3D dimensions that they're working through. And for humans, there's a whole set of issues of going to confined space. So that restricted maneuverability is very, very much an important area. And notice in this case from the World Trade Center, you're going down a drainage pipe to try to get into the basement. There's another regime where the agent is actually the environment smaller than the robot. I call that the granular regime. I think that's absolutely fascinating because that's where the robot has to burrow. It's no longer going through the terrain per se, it's actually burrowed. And I'm very excited to be working with Howie Chosen and Dan Goldman on a new grant to explore what Dan has been learning about how sand-swimming lizards burrow through the desert. And he's been looking at adapting that to robots and how he is adapting that to snake robots for disasters. And so we put those regimes together, you start approaching a quantitative model of what's characterizing at least the scale of the robot, of the environment, to the physical agent. And this can give us a common terminology to describe our robots. So here in the red area is granular, it's less than 1. The restricted mobility, we're less than 2. And then over here, anything greater than 2 is green. It's pretty easy. A human may have some gear or procedures, may not be able to go in for reasons. And so with that, you can start making predictions. So what is important for a robot to focus on? How can we look at that? So I'm going to skip over how to do the traversability, how we compute that. But if you just look at this ratio and say traversability, whether it's 2D or 3D, here this area is very easy. This part of the quadrant, this is where people can normally move in by themselves, So the robots aren't needed unless there's safety constraints. So that's like buildings are still intact, but you've got a chemical spill, a radiological spill, or a mine spill. And so that means that robots have to, the challenge is to actually make them not explosion-proof and explosion-proof and radiation hardened. When you go to the yellow regime, you're using the robots, they have to be more efficient than a person, because a person could still do the job, and if the robot is very painful to use, is not as efficient, is not fast, is not autonomous, then they'll back off using it. And then at the red region, well, at the granular, people can't do that. So that is just a very exciting region here. So let me wrap up and get back to the field work and your regimes and the things that you are working on, and get back to what we're going to learn today from you. So in summary, field work, as you well know, it's incredibly important, whether it's in a staged world or it's in the natural world. I recommend you collect all sorts of written data, robot sensor state data, but also try to collect observers' notes and camera views of what the robot is doing and what the team is doing. And for ground robots, please consider thinking about how we're going to characterize the agent and the environment, the scale, and the other dimensions. Can we come up with other dimensions numbers to help us compare and contrast what the different robots are doing? The observer sheet is available on request. Anything I have is yours. Please, if you have anything to contribute to Rescue Robotics, be happy for you to join Roboticists Without Borders, and I look forward to talking with you more and learning from you on this great session. Thank you very much.
Okay, so as we say in Australia, good day. My name is Raymond Shea. I'm from the Department of Computing at Curtin University in Western Australia, and I'm going to be talking about last year's Response Robotics Summer School, an event for researchers and research students on the challenges and the best-in-class solutions to the problems of response robots, focusing on the challenges faced by bomb squads. This was an event run by Curtin University in close collaboration with the West Australia Police Bomb Response Unit, the RoboCup Rescue Robot League and the RoboCup Federation, the National Institute of Standards and Technology, and Robo LLC. This event is an outreach event of the DHS NIST ASTM International Standard Test Methods for Response Robots project, which also includes the RoboCup Rescue Robot League itself, and is also the successor to a series of events dating back 10 years to the 2004 Rescue Robotics Camp. It's also the immediate successor to the 2012 IEEE RAS SSRR Summer School, held with the kind support of the IEEE Robotics and Automation Society. So this year's event was, I believe, unique, and I'm sure Robin can correct me if I'm wrong, in that this was the first time that such a summer school had been held in parallel with and co-located with a bomb squad commanders conference, in this case the Australian Bomb Response Technology Seminar, with about half of the sessions being held jointly. This had the great advantage that it allowed the responders to get a good insight into what was coming up in the research field and to help guide and influence it. And it also gave the researchers a very good opportunity to see firsthand the kinds of challenges that the responders are actually facing in their daily work. It also gave us the opportunity to be part of the practical sessions held using actual robots used in response, both in standard test methods for response robots as developed by NIST, as well as in operational scenarios, such as in this case, the response to a suspected clandestine drugs laboratory. So this year, we are also holding this event, this time around, like 2012, we have the kind support of the IEEE Robotics and Automation Society. And as before, we're trying something a little bit different. This time around, we're holding it at the Perth Artefactory, which is our local hackerspace, to try and get some cross-pollination between these non-standard developers and the academic community. We will also be using this as the opportunity to further develop and disseminate a couple of other initiatives that we're running to try and improve research in this area, one of them being the Confined Space Challenge, the RoboCup Rescue Confined Space Challenge, and the other one being the Open Academic Robot Kit. We look forward to seeing you at the interactive session.
Hi, my name is Stella Lacha. I'm going to be talking about the design of a 3-robot system called Herald, or the Hybrid Exploration Robot for Air and Land Deployment. This is intended for urban search and rescue applications. So this is the kind of problem that we're looking at. Large-scale urban disasters. We have 2 main goals here. 1, to potentially locate victims underneath rubble, which is a difficult problem. And 2, to survey the entire scene and make order out of chaos. The thing that we are competing with as roboticists is humans and their canine companions, and often just assisted by pole cameras. The problem with humans and canines is 1, that we don't want to risk their lives, and 2, that they get tired, and 3, that we have to extract them often expensively from dangerous disaster sites. So as roboticists, how can we improve upon this situation? Many people have attempted to make search and rescue robots that can effectively do the same things as human and canines. One of the most notable solutions are robots like the PackBot. They're effective at traveling over rubble, but they're often heavy, and they can ride over victims trapped under rubble. They cannot locate people underneath, and they cannot survey a scene from the air. Snake robots are very effective at going through cluttered environments, but they're not fast over large spaces, and they're not able to quickly survey a scene. Quadrotors are able to do this, but cannot operate in a cluttered environment. And the multi-robot systems that we've seen often don't solve the issue of locating victims beneath rubble. Our solution is a system of 3 robots, a quadrotor and 2 snake-like robots that can dock together with passive magnetic docking faces. This system is supposed to be used to locate victims beneath rubble, unlike a PackBot, and yet survey a scene. It operates in 3 main modes, the first of which is we call tank mode. Basically, the quadrotor is off when we want to preserve battery life. We drive 2 snake-like robots around on the ground, and this allows us to travel over spaces quickly and effectively. Here you can see a video of us driving up and docking. It's a quick and easy process. And driving around with the quadrotor off, this allows us to travel large spaces very quickly. We can also operate separated with 3 separate robots. So the snake robots traveling through rubble, they're small enough to fit in a 4-inch bore hole in the ground, and the quadrotor is able to survey the scene. Here you can see our quadrotor carrying 2.2 kilograms, which is roughly 5 pounds. The reason why it can carry so much weight is that we would like to be able to carry a single snake at a time, and I'll talk about that right now. Because the third mode we can operate in is called carrying mode. In this mode, we can carry a single snake over large obstacles, and especially things like stairs or other areas of a building. These capabilities together make us able to rapidly deploy the system through buildings and hopefully locate people more quickly. Thank you.
Thank you. My name is Kapil Katyal. I'm representing the Johns Hopkins University Applied Physics Lab, and I'm going to talk about a paper that we submitted that related to basically our approach to a robotic system that's used in a disaster type scenario. So we're all pretty familiar with the DARPA Robotics Challenge. The basic idea is you have multiple tracks, you have multiple either hardware, software implementations, and you have a variety of tasks that are used to demonstrate the capabilities of these robots in a disaster scenario. So we weren't part of the actual competition, but there was an exposition that was part of the DARPA Robotics Challenge that DARPA invited us to basically demonstrate similar capabilities in a disaster type scenario. So we basically wanted to highlight collaborative tasks and then disaster response scenarios that weren't already addressed in the DRC. And so we focused on 4 primary tasks for this competition, or for this exhibition. Extinguish a fire, which you can see there. Basically install a cervical collar brace, cooperatively place a victim on a spine board, and relocate the victim into a safe location. So we did this with our existing robotic platform called RoboSally. So RoboSally has a mobile base provided by Robotics. It has a 3-degree freedom torso, 2 anthropomorphic arms as its manipulator and end effector, and then a sensorized head that provides binocular vision as well as a time-of-flight 3D sensing capabilities. One of the key components of this is the manipulator and the end effector. So this is actually derivative technology from the APL modular prosthetic limb. So this is a limb that was designed for prosthetic use for amputees. Really, the significant components of this is that it's 50th percentile male size and weight. It also has human-like dexterity. It also has over 100 sensors throughout the hand for anything between force and voltage, position sensing, as well as tactile sensing at the fingertips. So in this approach, we looked at a variety of different approaches for controlling the robotic platform, from direct teleoperation through the glove, the Red Hawk system, which is an off-the-shelf controller, keyboard, mouse, as well as our supervised autonomy approach, which allows us to basically use computer vision to segment out the scene, find objects of interest, and use autonomous manipulation to help with the tasks. We've looked at a couple of different modes, and we figured out that basically what are the different modes that help depending on the specific scenario that we were trying to accomplish. We ended up implementing this architecture that allows us to select between the different modes on the fly, depending on the given task. And in the interactive session, we'll demonstrate videos of the system, description of the platform, different controls.
Hi, I'm Junichi Kura from Tokyo University. Today, I'd like to introduce initial trial about remote vertical exploration by active scope camera into collapsed buildings. This picture shows an example of severe disaster. In that case, we cannot approach from the side area, so we need to approach vertically from the above. We propose a remote vertical exploration with a crane system, which lifts a field unit to launch a tether robot into the labo. In this case, necessary capabilities for the tether robot are getting into narrow space smoothly and getting out from a deep area easily and selecting desired direction in the labo. We apply active scope camera as a tether robot. Active scope camera is a flexible video scope driven by serially vibration drive. And serially vibration drive also, driving forces are generated on the whole surface of the cable, and serial vibration also reduces its sliding friction when active scope camera is pulled out through the narrow space. However, active scope camera was not designed for vertical exploration. So our objectives are to design a new active scope camera for vertical exploration and to confirm the feasibility at a simulated collapsed building. First, we analyze the typical contact conditions for vertical exploration with active scope camera. We found the 3 typical cases. Then we tested the performances with such conditions, and to deal with no contact conditions, we designed a new headband mechanism. Finally, we conducted the experiment for the vertical exploration at the simulated collapsed buildings to confirm the feasibility of the proposed system. The active scope camera was inserted with a field unit using a rotating drum controlled by the remote operator. As shown in the video, the proposed system could explore into the deep area by changing directions. We successfully confirmed the necessary capabilities of smooth insertion, retrieve, and changing direction with the head pending mechanism. Please come and discuss with us. Thank you.
Good morning. I'm Gaki Minamoto from Tokyo University. The title of my presentation is Estimation of Ground Surface Radiation Sources from DOS map measured by moving dosimeter and 3D map. In 2011, the Fukushima nuclear power plant accident occurred. The radiation emitted from the power plant has spread across eastern Japan. Local spots of high radiation dose were created in residential areas and are called hotspots. It's necessary to detect hotspots by using dosimeters during the decontamination work because hotspots are invisible. In many cases, workers must measure the radiation over a long time. In this research, we propose a method to estimate high resolution and wide area map of radiation sources from radiation dose measured by moving dosimeters mounted on mobile robots or people, and 3D map of the environment. One of the problems of radiation source mapping is that the radiation dose is measured as discrete counts and has wide variability. This is because radiation rays originated from radioactivity K, which is a stochastic process, and the measurement time at each position is short due to the moving measurement apparatus. The right figure shows the time series of radiation counts measured in the movie. You can see it has to understand. To solve this problem, the proposed method estimates the intensities of radiation sources by computing the maximum a posteriori probability estimation based on the radiation characteristics. The radiation counts obey Poisson statistics and exhibit attenuation in accordance with inverse squared distance. The distance d is calculated from the 3D map and the position of dosimeter. This is one of the results of the experiments. The left picture shows the target area. In the movie, the green point cloud shows the 3D map of the environment. The yellow line shows trajectory of dosimeter. And the red point cloud shows estimated radiation sources. This shows that the proposed method can estimate radiation sources. I'd like to talk to you more in the interactive session. Thank you for attention.
Okay, my name is Kazuhiro Nakadai, working with the Honda Research Institute Japan. So this is a collaborative work by 5 institutes. So since the first speaker is now struggling with his startup, I make the presentation proxy for him. So I think that everyone agrees that robots should interact with people, and music-based interaction like dancing is one of the most enjoyable tasks. So this presentation focuses on assessment of musical genre classification in a noisy environment where a robot makes a motion noise like dancing. The purpose of this presentation is to make a robot dance to diverse musical genres in the real world. For this, we integrated musical genre classification with robot audition techniques like sound source localization and separation, which improves the quality of sound. Okay? For classifiers, we use 2 state-of-the-art techniques like SBM and VQMM, which considers temporal sequence of music. So these methods are evaluated in offline and online manner. For evaluation, we use more than 1,400 musical pieces, which have 6 manually annotated genres. For metrics, we use F-measure with 10-fold cross-validation. So these figures show the result. And actually, the sound source separation drastically improved the performance in both cases. It's like 40 points. Comparing 2 methods, SBM slightly outperformed VQMM, but VQMM is more suitable for online processing because it requires only 3-second data for training. In the last minute, I'd like to show you a demo. The robot has 16 microphones on the top of the head, and the speaker plays the music. I'm sorry. Okay, probably you don't know what is world like, but anyway, so for more details, please visit my poster session. Thank you for your attention.
Hi, I'm Takuma Ohata. I will talk to you about outdoor sound source detection using a quad rotor. Computational auditory analysis in an outdoor environment has been actively studied in the past few years. For example, it is useful to find people in disastrous situations. Because it is crucial to find people as quickly and widely as possible. Using a quad rotor is suitable. However, there is a problem in outdoor auditory analysis using a quad rotor. The sound of quad rotor is very noisy. Please look at the video. It is very noisy, as you can see. So noise robust sound detection is necessary. This is a microphone array embedded quad rotor used for sound source localization. We have reported a sound source localization algorithm called IGVD music. With this method, the noise is suppressed using signal and noise correlation matrices. We show that it works properly. However, there are still two problems. One is that K inverse R is not an elementary matrix, and the other is that K is sometimes overestimated. Both lead to performance degradation. So we propose IGSVD music with CMS to solve these problems. This method uses GSVD instead of GVD to be applied to non-elementary matrix, and the overestimation of K is relaxed by soft whitening using alpha. The results look like this. This figure signifies reference. These black lines are correct utterances. With IGVD, 6 utterances are correctly detected, and 3 were misdetected, shown in this figure. The proposed method drastically improved the performance of localization. In this case, the performance improved from 67 to 89%. Please visit my presentation if you are interested. Thank you for your attention.
Sorry, I'm Ian of Kyoto University in Japan, and the title of my presentation is Visualization of Auditory Awareness based on sound source position estimated by depth sensor and microphone array. And first, I explain the research background. Visualization of acoustic environment is important for intuitive seeing understanding. The existing visualization is basically a combination of music spectrum image and RGB image captured from microphone array and a camera as shown in this figure. But we believe this visualization lacks two kinds of auditory awareness. The first one is spatial auditory awareness. As you can see in this figure, it is difficult to recognize which sounds are from the target. And the other is temporal auditory awareness. We believe it is difficult to understand temporal changes of the target sounds. So to solve these problems, we use depth data as shown in this figure. In this study, we propose 3-layer model for visualizing auditory awareness. This model has 2 additional layers. And the first one is sound location layer. This layer provides spatial auditory awareness and shows sound with target location. And second layer is sound saliency layer. And this layer provides temporal auditory awareness and shows temporal changes of the target sounds. And then let me explain the behavior of each layer. First, in sound location layer, object shapes are estimated from depth data, and we can select the target to be focused on. For example, in left image, we select this person as a target, and then the acoustic information is visualized on his shape. Otherwise, in the right image, we select this laptop as a target, and the acoustic information is visualized on its shape. And next, in sound saliency layer, from left image to center, if there are no temporal changes, so the color becomes thin. On the contrary, from center image to right, if there has temporal changes, so the color is emphasized. With those additional layers, user can flexibly select the sound source target and can intuitively observe the target behavior. Conclusion is here. More detailed explanation in a given poster session.
Hello, my name is David Grunberg, and I'd like to talk to you about my research involving enabling robots to listen to musical audio and identify and learn the beat locations, even despite the presence of heavy noise. Now, there are many circumstances in which it is useful for a robot to be able to listen to and observe some sort of repeated periodic thing. In particular, my research group is focused on teaching the robots to learn where the beats are in music. Why? We're interested in enabling robots to perform music alongside humans, to make human-robot musical ensembles. In order for this to be a possibility, though, the robots have got to be able to listen to the human musical performances and extract certain high-level features so they can intelligently create their own performance which fits with the humans. One such feature is the beat. If the robots can't learn where the beats are in the humans' music, they won't be able to synchronize their music with the humans, and it won't work. Now, but there's a problem. While many beat tracking algorithms have been developed in the signal processing community, particularly in the field of music information retrieval, most of those algorithms, they tend to work best on audio that is very clean, say taken directly from a digital file or CD, produced in a studio, professionally mastered, and so forth. You can see an example of that in the top spectrogram here. This is just a regular audio file, and the beats are very obvious even to us, these big red steady columns. Add noise into the picture, and suddenly it doesn't work so well. A noise can obscure the beats in the spectrogram and the acoustic signal, make it very hard for existing beat tracking systems or to figure out where those beats are. As you can see in the bottom spectrogram, which is the same music but with some robot noise added in, the beats are much less visible. In order to work on this problem, I'm using a system that incorporates probabilistic latent component analysis. This is an algorithm that can decompose a signal, such as an acoustic recording, into the elements that comprise it. So if a robot hears music containing, say, a beat instrument, such as drums, other instruments, noise sources, and so on, PLCA can be used to break those apart and assign each of them a different component. The system can then analyze each component to determine which of them is the most probably corresponds to a beat, and can identify the spectral characteristics of the beat for that particular music. Once that component is known, the PLCA can also be used to find the probability of that component being active at any given frame. Because, obviously, if the component is active, there's more likely to be a beat there than not. That can be used as a useful accent signal, or a signal which tends to correspond to the beats in the beat tracking parlance for a beat tracking algorithm. The accent signal can then be passed into a periodicity detector to estimate the tempo, such as, say, autocorrelation or correlation with impulse trains spaced at various distances. And then that can be used in order to find the beat locations, thereby enabling the robot to determine where the beats are, again, even if the music they're listening to is contaminated by, say, noise from a noisy robot moving its arms in time with the music. Our algorithm was then tested against several others, just off-the-shelf beat tracking algorithms in the field, and as you can see from this histogram, the proposed system worked better on noisy audio than the off-the-shelf systems. I'd be happy to talk to you more at the interactive session. Thank you for your time.
So good morning, everybody. I'm Yanni Even from ATR in Japan, and I will be presenting this work. So here, as we can see in this small video, we are concerned with corridor and especially with blind region, because when we use sensors that require line of sight, like LRF and camera, here the problem we had is that the person is just detected at the last moment when coming out of the blind region. So what we want to do is actually to anticipate the arrival of the person. To do so, we will be actually using sound, because even if we cannot see the person yet, we can already hear that person. So the thing is that we can hear the sound because there are some reflections that leaks out of the blind region of the line of sight sensors. So we want actually to detect this reflected sound and then trace them back to the origin in the blind region. So this is actually made. To do it, we need actually first to estimate the direction of arrival of this reflected sound that came out of the blind region. Then we will need to have a 3D representation of the world that contains information about the normal to the surface so that we can do this audio recasting. And of course, if we want to use the map, we need to know where the robot is in the map. So we need also to localize the robot. So this is why the type of sensor we are using are actually wheel encoders and laser to create the map and also to localize the robot. And we also need to have the microphone array to estimate the direction of arrival of the reflected sound. So combining all of this, we are able actually to compute in real time the acoustic ray and trace them back into the blind region where we get the intersection of those rays. And by making a 3D histogram of this intersection, we get some information about what is happening in the blind region. And especially, we found that the local maxima of this distribution of intersection give us information about the sound source position in the blind region. So if you want to hear more about that, you can come to the interactive presentation that I believe will be in Salon 10. Thank you.
Hi, I'm Mitsuru Kamizaki from RSJ University, Japan. Today I'd like to talk about adaptive basic I/O gain tuning method for human-machine systems. So as is well known, the I/O gain, which defines the relationship between operational input and actuator velocity, is largely affect the work performance in the human-machine systems, such as surgery assistant robot, construction robot, or many kind of teleoperation systems. So many types of gain tuning methods have been developed. The most of them focused on simple matic adjustment in almost unknown environments. So by contrast, this study focused on fundamental adjustment in unknown environment and operators' characteristics. So which means the automatic adjustment of the most fundamental I/O gain in human-machine system based on the comprehensive tendency. So to distinguish conventional gain, we call this basic input-output gain BIOG. So this figure shows the framework of BIOG tuning system. So we think it's comfortable for an operators when the operators evenly uses the entire range of the control lever. So we adapted the lever histogram as a control variable. And BIOG 2 point is an operating variable. And the normal distribution is a target values. So the tuning rule is to eliminate the excessive bias of the frequency by regardless the operators, the work contents, regardless, So this conformation provide the machine operators with consistent operabilities because they can control the machine with same operating feelings. So even if the work contents and work environment is changed. So with 2 types of experiment is conducted using the hydraulic systems. So the results show the time efficiency improved while increasing the subjective usabilities by conforming the lever histograms to normal distributions. So I will explain the tuning system and experiment in more detail in interactive sessions. So thank you for attention.
Today, I would like to talk about the remote robotic volcano observation. My name is Genki Yamachi from Tokyo University. In Japan, there are 110 active volcanoes, and this Mount Asama is one of them. Once a volcano erupts, a restricted area is set like this red circle. In such situation, it is difficult to observe the circumstance of the volcano inside the area. However, the information is very important to reduce the damages by volcanic eruptions, such as a debris flow. To overcome this situation, the Ministry of Land, Infrastructure, Transport, one of governmental organizations in Japan, contacted us the possibility to use a remote robotic observation system in such environment for predicting debris flow. For the prediction, the most important information is an amount of piled ash, volcanic ash. The information can be just pictures before and after of eruptions. To obtain images is our objective of this research. This is our scenario of the remote robotic observation system using multi-rotor UAV and a small ground vehicle cooperatively. On the next slide, I would like to focus on the landing system of the ground vehicle in this scenario. Our multi-rotor UAV navigates autonomously based on GPS information, which includes height errors. To make our system very simple, we do not choose sensor-based height control system, instead tethered landing system. It has no power source such as motors, but contains our tether, wire, and a rotary damper that reduces the falling velocity. Finally, when the vehicle touches down, the tether slips out.
This is our recent field experiment, September 2030. The departure location was at elevation of 1,900 meters in Mount Asama, and the target was at 2,100 meters. The distance was about 600 meters. Nylon wire was used for our tether for the sky crane system. In the next interactive session, I would like to explain the sky crane system and our project in detail. Thank you for your attention.
Yeah, hello everyone. My name is Jae Kim, and I'm a PhD student from Chungnam National University in South Korea. As you can imagine in this title, we wanna just know what is the best way for wheeled robot to traverse rough terrain efficiently and rapidly, and of course safely. Because there are a lot of challenging issues facing wheeled robots on rough terrain. First of all, the robots have to deal with two kinds of characteristic changes of rough terrain. First is the change of soil types, because the surface is composed of various soil types, such as firm soil, gravel, and glass, and so on. So second is the change of surface shape, because the geometry of terrain is different, like slope. So there are many robots to traverse rough terrains for various purposes. As you know, Curiosity on Mars for planet exploration, and Crusher for military use. So these robots have tried to overcome these kinds of characteristic changes on rough terrain by solving such the main issues through the researches on terrain classification and optimal driving control. So in our study, we are focusing on main topic among them. So it is to develop an optimal wheel slip control algorithm in order to maintain maximizing traction and to maintain a balance between maximizing traction and minimizing energy use while following desired velocity. So this is the overview of our proposed algorithm. So the key parts are in red boxes. So soil identification and slip optimization and neural network part. So this is a video to show you our driving performance of our proposed algorithm. This video is about general balance control. So this robot was in a big trouble on loose soil because of unexpected wheel slip. But in this case, this video is about driving performance of proposed algorithm. This robot is working well.
Good morning, my name is Seung Yang. I'm a master course student in Sungkyunkwan University, Korea. Today I'm going to present about novel robot mechanism capable of 3D differential driving inside pipelines. In most industrial facilities, pipelines are prerequisite for transporting gas, oils, and fluids. They are required periodic maintenance and inspection. So InPipe robot is developed to explore and inspect pipeline. To do this, we have problems for solution. First, when the robot travels in curved pipeline, each wheel has different paths. How do we control each of wheel velocity? Second, brake mechanism is needed to overcome the slipped wheel. Third, ability to climb a vertical pipe is required. Finally, we want to rescue the robot in emergency. To solve the problems, we applied 4 mechanisms. In this way, MR-Inspect 6 Plus is developed. First, multi-axial differential gear has a single input and multiple output. It provides different velocity in curved pipeline without any control effort. In straight pipeline, these alpha gears rotate in the same direction with exactly the same velocity. In curved pipeline, these alpha gears have different velocity. Second mechanism, active work pressing mechanism. It changes the size of robot and generates the work pressing force. Third, rescue mechanism. The robot can be pulled back by using gear shift mechanism without any damage. Finally, brake mechanism. If one of the wheels is slipped, the brake mechanism prevents the power crossing by braking the idling wheel and transfer the power to the other wheels. Driving experiment is carried out in acrylic pipeline. This pipeline consists of horizontal, vertical, and elbow. As shown in the video, the robot operates well as expected. As related to the paper about sensor module of our IMPACT robot project is also accepted in this conference. You're welcome to my interactive session. Thank you for your attention.
Okay, so hello everyone. I'm Hong La from University of Nevada. I'm here to present our work for development of autonomous robotics system for bridges inspection and evaluation. So currently we have about like 6,000 bridges, and 1,000 of them have poor conditions and easy to collapse. And unfortunately, the bridges, it's manually inspected. For example, like you see in this video, we have very well-trained engineer who drag the train along the bridge deck and detect the defect area. Then by listening the non-autonomic sound, or we have a bunch of people carry different ND sensor to inspect the bridges. So this kind of not efficient method and time-consuming, and also prone to human error. And of course, it is very dangerous job because it's open traffic. So this motivated us to develop our robotic system that can autonomously travel on the deck without human monitoring. So it can inspect the bridge simultaneously. So the robots integrated with a lot of non-destructive evaluation sensor, like a ground-penetrating radar here that can detect the corroded rebar inside the deck. And also it have the acoustic array to detect the hidden crack inside the deck, and the electrical resistivity to detect the corrosive environment. So this robot is like a doctor to check the health of the bridge deck. And we develop our motion planning, the velocity controller and heading controller to allow the robot autonomously travel on the deck and also to avoid the obstacle. We also develop our extended command filter to allow the robot to localize precisely without 2 centimeter error on the deck, because it's very important. If the robot go out of the inspection area, it could cause, it could make accident to the traffic. So here you see the results of the robot. It can build the condition map of the bridge in real time. You can see the red area is the defected area, and also it can build a crack map based on the statistics image by the front camera here, and all the crack is built and mapped to the real bridge coordinate. And you can zoom in and see hair side crack, the location on the deck. So for more questions, we can discuss in the interaction. So thank you very much. Yes.
Good morning, everyone. My name is Endo. Today, I'd like to talk our decontamination method and system for realizing it. Let me begin with talk about the background. TEPCO Fukushima first nuclear power plant broken on March 11, 2011, by large earthquake and tsunami. And nuclear power plant blew up and spread a lot of radioactive substances, as shown in this figure. Day by day, the radiation dose became lower. Almost all of area around Fukushima has acceptably low level. However, the effect of long-term exposure to very low radiation level is unknown. So we must make an effort to reduce the radiation level as much as possible. Generally, workers decontaminate the road surface following the guideline published by the Ministry of the Environment, Japan. By this method, only 60% of radioactive substances are removed because only radioactive substances on the surface are removed and radioactive substances in the surface are remained. On the other hand, we propose a method using the same small instrument with generally method. Based on fluid dynamics, the washing nozzle positioned very near from ground to grind the surface. Specifically, the distance between the nozzle and the surface of the ground is set 10 to 20 millimeter and spend 50 minutes on each 1 meter square. By this method, not only radioactive substances on the surface, but also in the surface are removed. However, the high precision is required to position the nozzle on this method. So, we developed a washing robot system. And a simple algorithm based on the spring mass damper model is implemented on the robot to keep the distance between the nozzle and the decontaminating surface. Using the system, we did an experiment in the field which had already been decontaminated by general method. It means 60% of radioactive substances were removed. By using our system, we achieved additional 30% removal. Thank you for kind attention. I'm looking forward to talk with you at the interactive session. Thank you.
All right, good morning, everyone. I just want to start out by saying thanks for the opportunity to come out and present. I appreciate everyone coming to listen to my 3-minute car salesman spiel here. My name is Jeff Durst. I'm with the U.S. Army ERDC. And today I'm presenting some work done called a Framework for Predicting the Autonomous Mission-Specific Performance of Unmanned Systems. And it's done in collaboration, you can see, with quite a few co-authors from a NATO work group. So to give you a little bit of background, this was done by a NATO Applied Vehicle Technology, or AVT work group. And these are basically work groups endorsed by NATO to address a specific need in the S&T community. And in this case, it was the problem of no real definitive measure exists for measuring autonomy. There's the ALPHAs and several others, but they aren't quite formalized. And in particular, kind of compounding the issue is there's absolutely no measure of how autonomy affects mission-level performance, because I'm sure we've all experienced you make the robot smarter, it actually does a worse job sometimes. So that was the goal of the AVT 175, was address this problem, define autonomy, levels of autonomy, and specifically how do hardware and software technologies impact autonomous performance. So just a little background for those not familiar. Here's the ALPHAs. It's a 3-axis system. You have mission complexity, environment, and human independence, and it basically combines test scores for each axis into one number. And the important thing to say about the ALPHAs is this is a retroactive measure of how a system performed for a specific mission with a specific operator, which is not sufficient for us military guys, and it doesn't quite meet our needs. So we came up with a new framework called Mission Performance Potential, or MPP. And the way this works is it's sort of the opposite of the ALPHAs. What we want to do is look at just the characteristics of the system, and I'll kind of explain these acronyms in the interactive session, but the idea is just looking at how big is it, what's its mobility, what software does it have human detection and mapping, SLAM mapping, just the basic system components, and then take an environment description and a mission description and use some scores, some weights, some mass, and using fuzzy logic, come up with here the final MPP number to predict what you would expect the performance to be at a specific autonomy level. So these are things like, does it have to operate in soft soil? Is it vertical takeoff and landing? How big is it? And right here you have the environment, cross-country on road. So if it can't operate cross-country and you have to operate cross-country, it's automatically a 0. So here's just a couple of comparisons and contrasts of the MPP and the ALPHAs. I hope to see you guys at the interactive session to talk more about these. And like I said, the most important is over here we live in the predictive side of this hardware, this software, this mission, how well do I expect it to perform given its level of autonomy, and this is for a specific system and a specific mission, what was the autonomous performance. So thank you very much.
It's on the screen here. Okay, great. Good morning. I'm Jonathan Fink. I'll be presenting work I did with my collaborator Ethan Stump at the U.S. Army Research Laboratory. Our work is titled Experimental Analysis of Models for Trajectory Generation on Tracked Vehicles. This work represents the first step towards a system that's going to allow autonomous, robust operation in challenging environments like the one pictured here. We're particularly focused on models for tracked and other skid steer vehicles due to their reliability and ability to deal with a wide range of terrains. While there's extensive literature on detailed modeling of the track-ground interaction of larger vehicles, we're specifically interested in small vehicles operating at high speeds, the limit of their capabilities. So why is this problem hard? First of all, correctly modeling the tracked vehicle motion is a hard problem involving intermittent contact mechanics, friction, shear deformations, and you quickly enter the realm of continuum mechanics. Even dealing with homogeneous surfaces like the ones you see here, just a concrete floor, present a lot of challenges for modeling this behavior. One approach would be to rely on feedback in the system, but there's two main issues that we run into. First, there's no obvious error signal we can use at the rate and scale of a single rapid maneuver. If we were to look at GPS, it would be too coarse. If we were to look at vision-based odometry systems, you're dependent upon favorable feature-rich environments, and inertial navigation systems are going to be too bulky and expensive for the types of systems that we're interested in. Secondly, feedback requires you to have an understanding of the relationship between your aerodynamics and your control signal, and that relationship can be linearized. The systems we're interested in are subject to motor saturations, time delays, on top of the nonlinear effects that you have for the train interaction. Previous work has focused on how you can explain trajectories over entire missions, the odometry problem essentially. We're interested in the related problem of trying to take a time-varying control input and then be able to predict the motion over a relatively short time horizon. In particular, we study the statistics of those motions over repeated executions. To that end, we'll be considering 3 canonical trajectories, a left turn, a right turn, and an S-curve, and then looking at data captured with the motion capture system over many runs again to look at model uncertainty. We can use that data to fit a dynamic model for the motors, and we'll examine several different kinematic slip models of higher order. And then finally, we can use this to optimize control inputs and allow us to better track desired trajectories. And you can see some of our results here, and we'd be happy to share more with you at the interactive session.
So hello, everybody. My name is Natalia Ortoz. I'm coming from University of Girona. And today I'm going to present the work entitled Sonar-Based Chain Following using an autonomous underwater vehicle. This work has been carried out in collaboration with our colleagues in the National Technical University of Athens. So the motivations for our work come from the monitoring of mooring chain integrity, which is performed regularly through inspections to ensure the ship safety. So these inspections require a prior step, which is the removal of the marine growth, which is accumulated on the chain links. So this is typically performed through divers or remotely operated vehicles, but we want to propose a cost and time effective solution for cleaning mooring chains that it's based on using an autonomous underwater vehicle equipped with a water jet and a forward-looking sonar so we can operate under turbidity conditions. So while we have other works dealing with the robust control of the water jet perturbations, in this work we are focusing on the detection and following of the chain using sonar imagery. So our system is basically composed of 3 main modules. The first is the chain link detector, which is in charge of detecting the different links on the challenging forward-looking sonar images. Then these detections are clustered in waypoints through a planner, and the control module is in charge of guiding the vehicle through these waypoints. So here we can see a simple example that we perform in our water tank using a mock-up of a chain, in this case deployed horizontally. Since the feature detectors are not working very well on this sonar imagery, what we do is we extract local template matchings through cross correlation, and we take profit of the high frame rate of the sonar to accumulate them over time. And knowing these detections and the link dimensions, we can extract the more probable locations for the link centers. So these noisy detections are then clustered in waypoints that the vehicle keeps following one after the other, while at the same point is keeping the orientation towards the farther detected links in the field of view, so as we don't lose the next upcoming part of the chain. So this process is basically repeated until we reach the last waypoint of the chain, and we conclude the following. So we have obtained an accurate trajectory over detected link centers, and these detected link centers actually lie very close to the real link locations. Finally, a side outcome of our system is that we can obtain a high-resolution acoustic mosaic by registering the acoustic imagery gathered along the chain following, and this mosaic can serve as the means to perform a first visual inspection of the chain state. So that's all from my side. I'll be glad to answer further questions in the interactive section.
Hi, I'm Chris Jones. Thank you all for sticking around to the end of this session. I'm from iRobot Corporation and wanted to just say a few words about some of the R&D work that we're doing that you may not be familiar with, to put it out there to show where we're going in terms of commercializing technologies that you're seeing presented around the conference here, where that path forward is in different product lines. So I'll share a little bit about that for you, and also to point out that we're hiring. So we have a lot of openings. So if you're you're graduating, you're looking for an opportunity, please contact me or look us up. Many of you may know kind of our products from the consumer side, like Roomba. We have some remote presence platforms and defense and robots for defense and law enforcement that you've seen throughout the session. On the technology side, we have an active pipeline of work, R&D work that's going on that will be enablers for next generation technologies, specifically in the area of navigation that I'll talk a bit more about, but also including cost-effective, practical manipulation capabilities for the home or office environments. We have an active amount of work there. In cloud robotics, of course, how to, once the robots are more and more connected, how do we leverage the broader ecosystem of computation, of data, of third-party services, et cetera, to enable value in future robot products. So these are very important to us in areas that we're actively working on. On the navigation side, so in particular, looking at the consumer product side of our business, the convergence of technology that can make it feasible to have intelligent navigation even on consumer products is reaching a tipping point. We have had years of work going into navigation technologies in this area, including visual navigation. So we believe that there's a lot of opportunity for intelligent navigation using commodity cameras and visual SLAM algorithms to be real enablers for future robot products. So this is an area that we are putting a lot of value in, and please talk to us if you're looking for opportunities or collaboration in this space. We also have work in commercial robots. These are robots for the enterprise environment, Fortune 500 companies, hospitals, et cetera, where we do actively deploy autonomous navigation on these robots. So there's FDA-approved autonomous navigation for these robots in hospitals. That's very exciting, and we continue to advance and look for opportunities to advance the intelligence of these platforms in these markets. So please, thank you for your time. Come join us, help us develop these next generation technologies. We have internships, full-time positions available. Please talk to me, and I can talk later as well. Thank you.